Hello, everyone. Thank you for joining us today for the introductory session to Barracuda Virtual Reactor by CPFD Software. This is the newest solution to join the Altair Partner Alliance, also known as APA. A few housekeeping notes before we begin here. The presentation is going to last for about 30 to 40 minutes, and afterwards we will have a question and answer session where you can ask, your questions, but even though the lines are muted right now and will be muted for the entire webinar, you have the option to type your questions into the questions tab on your GoToWebinar panel. So please feel free to use this chat box or question box anytime during the presentation, whenever the question comes up, and the questions will then be addressed at the end of the session. If you have any general questions about the Altair Partner Alliance, feel free to ask them as well. We are also able to type in answers to the panel if we can do so during the presentation. This session is also going to be recorded, and we will post it on the Altair resource library later, and the CPFD folks will also post it on their website, so you can watch it again or share it with your colleagues later. And you will also receive an email with the recording link sometime after the webinar, so you won't miss it. If you want to learn more about today's product, please also visit the web address on our Altair website. You can see it here on the screen, altair.com/barracuda-virtual-reactor. And with that, I come to today's presenters. We see them here on my slide. It's Peter Blazer, the Vice President of Operations at CPFD, and Sam Clark, who will do the demo today, and he is the Barracuda Virtual Reactor Product Manager at CPFD. They will be able to give us an in-depth insight into the company and into their product, and I'm so happy that they're here today, and I welcome you, Peter and Sam. We're happy you can present to us, and with that, I'm done with my part of the presentation here, and I'm going to give the presentership to you so you can share your screen and start your presentation.
All right, well, thank you. I'll just get the screen sharing. And Sarah, is that coming across?
Yes, looks perfect.
Okay. Well, hello, everybody, and welcome. Again, my name is Peter Blazer, and I'm thrilled to speak to you today about Barracuda Virtual Reactor, unlocking the power of multi-phase simulation. What we're going to be speaking about today is I'm going to begin by going through an overview of CPFD software, the product Barracuda Virtual Reactor, where it's applied. We're going to quickly look at 3 different use cases in different application areas, different industries. Refinery risk reduction, we're going to look at decarbonizing the cement industry, scale up of a waste gasification process. I'm going to then hand it off to Sam, who's going to do the live demo, and then we're getting to that Q&A. I will encourage everybody, as I'm speaking, as Sam's doing his demo, please put your questions into that questions panel, and that'll make our time at the end go smoothly. So, who are we? CPFD Software. We are advancing multi-phase simulation and technology, and this is specific for fluid particle systems such as fluidized bed reactors. The product, Barracuda Virtual Reactor, models the 3-dimensional transient fluid particle hydrodynamics, the heat transfer and chemical reactions in industrial scale units, and we're thrilled that this is now available on APA. So all APA-enabled Altair customers have access to this today. The software is used to improve reliability and performance through simulation. So for an operating unit, which typically operates 24/7 for years on end, it's used to virtually look inside and determine what's happening, root cause of underperformance and other phenomena, reducing the risk of then making changes to these units through virtual testing, and invariably our clients find other optimization opportunities in the process. And then for customers that are developing new technology, especially those, we'll get to this in the sustainability space, It's used to broaden the research, the R&D process, and then more quickly and at lower risk, commercialize, scale, and bring that technology to market. The product virtual reactor, it is physics-based engineering software package. It's really the only commercial software that's focused specifically on chemically reactive fluid particle flows at full scale, at full industrial scale. It's self-contained. It's got a graphical user interface. It's the solver. The post processor is TechPlot for Barracuda. I'll mention more about that in a bit. Parallelized using NVIDIA GPU and multi-GPU technology. There's two broad classes of problems, of applications to which Barracuda Virtual Reactor is applied. The first is gas phase domains with particles. So here I'm showing a fairly small FCC regenerator. This particular unit is something like 20 feet in diameter, 75 feet tall, but it gives you a feel for the scale when I say industrial scale. These types of applications, and up until about a year ago, this was almost exclusively, every Barracuda calculation was for gas particle systems. So the gas phase is compressible. You get multiple gaseous species. There's no limit to number of materials in the gas phase and the particle phase droplets. The particles, the droplets, are discrete Lagrangian. Again, I'll say more about that in a bit. No limit to the number of species, no limit to the number of components, full particle size distribution, and then that gas particle motions coupled with the thermal calculations and multi-phase chemical reactions. And then last year, we're super excited to announce that we've expanded, really doubled the application areas for virtual reactor from two-phase to three-phase system, vapor, liquid, solid systems. So this new class of problems is really liquid phase domains with both particles and bubbles. This sample ebulated bed reactor on the right, here we have a 12-foot vessel, 120 feet tall. It is a liquid fluidized bed of catalyst. Through it is our bubbles moving. So here the carrier fluid, the liquid, is incompressible, three-phase, there's no limit, similarly to the number of materials in the liquid. In the discrete phases, the particles, bubbles, no limit to the number of bubble species or particle species, and similarly full size distributions, coupled with thermal and chemical reactions. And there are broad application areas for virtual reactor. Historically, probably refining has been the biggest application area, specifically the FCCU, the fluidized catalytic cracking unit. Close to that are petrochemicals, polyethylene, polypropylene, catalytic dehydrogenation processes. Gasification historically had been coal and petroleum coke, but more recently are things like biomass for renewables and municipal solid waste. Materials and chemicals, this could be cement, ore roasting, titanium dioxide, go down that type of list. The commonality is fluidized bed reactors. Power generation has been circulating fluidized beds, typically also various emission control systems. And right now, I would just say the last few years, we've had our biggest growth in, I list clean technologies and renewables there, but this is really a wide range of applications in the renewable sustainability decarbonization space. Things like taking municipal solid waste and making jet fuel, hydrogen production, advanced recycling of plastics, carbon capture. We also work with researchers in general fluidization, and I wrote other here. This could be the liquid solid space, things like ebulated beds, slurry beds, bubble columns, and really a diverse set of fluid particle systems. We've been honored with a lot of recent recognition. I'm not going to go through all these, but if you look at the bottom first, in 2019, the iChemie Global Awards recognized, highly commended a project we did with Viva Energy Australia in the refining space. In 2020, it was a different project. It was actually in the renewable space with TRI working on gasifier, turning municipal solid waste into jet fuel. We'll talk more about that in a moment. 2020, we were also the winner of the Best Software Technology from Hydrocarbon Processing Awards. And in the last 2 years, There's been a recognition of the shift towards sustainability applications and the impact we're making together with our customers in bringing these much needed technologies to market quickly. I'm going to quickly go through what's unique to Barracuda Virtual Reactor and a brief list here of features. I'm going to say it here. Sam's going to come over and demo this in a moment. This is not everything, but there are some things that make us unique. And the first here is discrete particle properties. This is something that's really important to fluid particle systems, to fluidization. It's not just the particle size that matters. It's also the distribution. Fines content can take a fluidized bed from a turbulent well-mixed mode to a gas streaming mode due to lack of fines. And in Barracuda, each particle is a discrete Lagrangian entity, and you have millions or tens millions, in some cases hundreds of millions of these. So very naturally, it's easy to get things like your particle size distribution. That's an input that can evolve. And it's not just particle size that's discrete, but also the temperature. Each particle has its own temperature. Each has its own composition. Each has its own history, resonance time, and so forth. And again, I'm going to say this, Sam's going to demo it. If you have questions, because I'm doing this high-level overview, don't even wait till the end. Just go ahead and put those in the questions panel, and we're going to get to that. The next distinctive here is the Barracuda is able to handle the full range of solids loadings. This is an older video of an experiment next to a simulation at a test run out at the NETL laboratory, National Energy Technology Laboratory. And what you see here is regions that are fairly dense, more bubbling, some turbulent, some very dilute systems, some areas where there's no particles at all it handled in the same simulation at the same time without knowledge in advance of where things are to be dilute or dense. The whole range of solid loadings is able to be modeled there. And that hydrodynamics is coupled with the heat transfer, the multi-phase reactions. Here's an example from an FCC riser where you have regenerated catalysts coming down, going through a dense phase lift, and then very rapidly moving up where you have the hydrocarbons being sprayed in. Here's the heat transfer, so you have the thermal behavior. Here you have the hot regenerated catalyst getting impacted by the cool feed that vaporizes and the cracking reactions, cooling as it goes up. And then the multi-phase impact on the species. So through reactions, you have a vaporized gas oil going to other gas phase species. But notice also the reactions are affecting the particles. In this case, it's a coke being deposited on the catalyst. And so this is what Barracuda Virtual Reactor does. And on top of the hydrodynamics is model the thermal and the multi-phase reactions. It's built for industry. Industrial units are large scale, have many, many particles, and the assumptions and a lot of what we've done has made it feasible to run these large scale industrial units in a practical, meaningful time frame. Part of how we do that is through GPU and multi-GPU acceleration. So we are a preferred partner with NVIDIA. In fact, we were an extremely early adopter of GPU technology, releasing our first GPU parallel code in late 2013. For those of you that don't know a GPU, this isn't the place to go into all of it, but basically here is a particular GPU. CPUs have, they have lots of cores now, but it's typically, the tens, maybe up to 100. GPUs now have thousands and even tens of thousands of compute cores on a single card. You can have multiple cards in a box. Here are some speed up graphics from about 2 years ago when we first released our multi-GPU version, looking at a DGX workstation that actually fit under your desk, had 4 of these A100 cards in it. And we saw anywhere from 50 to 400 times faster than CPU just on that station. Now the benchmarks are even faster. We've seen over 1,000 times faster. You can run Barracuda Virtual Reactor on premise or on the cloud. And if you're not familiar with GPU, we got lots of partners that can help you get started with that, both on premise and on the cloud. The post-processing is powerful and extensible. So powerful comes bundled with Barracuda. It is Barracuda. It comes bundled with TechPlot for Barracuda. Really an industry-leading post-processor for visualization, graphics like this. Sam's going to demo that in a moment. But you can also dump your raw data out. You have full access to that. You can process that with various analysis scripts. And we are here to help. So as an APA user, you can also log into our support site, get access to knowledge base articles, user manuals, how-tos, access our training programs. But you can also speak to a human. We closely work, we pride ourselves on getting our customers successful, and we want to see that happen with you. I'm going to go through 3 quick use cases and hand it over for the demo. These are all, there's extensive publications and details elsewhere. The first one is refinery risk reduction. So here we have an aerial view of the Geelong refinery in Australia. And one of the units you see here, not the big tanks, is it's called a fluidized catalytic cracking unit, or FCCU. They made some changes at a turnaround. And by the way, everything I'm going to say in each of these examples, you're going to find a source down here. You can click on that and find more details. I'm giving you the real high-level view. They made some changes in 2011, and they had some temperature excursions that would happen. Not all the time, but they would start to run away to the point where the operator had to intervene, pull back feed, and to the point where they were limiting throughput for various crudes going through the refinery. And it was costing them tens of thousands of dollars a day. So what do you do? Well, let me put it into scale, put it into context here. Here is the FCCU. This is called a regenerator catalyst. Burns the coke off it burns the coke off the catalyst there. Over here is the reactor. Next to it's a distillation column. Large scale unit, runs 24/7 for about 5 years on end. And then you have a chance, you shut it down, and you're making a change. What change do you make? What change in the past led to the issues, and what changes will correct it? What might make it worse, and what are not needed? So what we did is we made a model in Barracuda Virtual Reactor of the regenerator. And you're just looking at some sample output. On the left, we have the catalyst hydrodynamics, the big, and this is a larger unit, well over 30 feet in diameter, I would say, at the bottom. So we have the catalyst moving. Next to it, you see some temperature variation. On the white-blue color scale, second to the right, that's the oxygen, running high excess oxygen through it. And on the very right, in the green, is carbon monoxide. And this is the aha moment. It should be a full burn unit with no CO exiting. You do see it asymmetric, leaving the unit where it combusts with the excess oxygen. That's your temperature excursion. Using this information, the engineers could then decouple which changes would make this better or worse, test ideas virtually, came up with a redesign that we tested prior to implementation, and then they implemented it. The simulation indicated the changes would be beneficial. They're implemented in 2016. And the outcome, they compared 12 months of operational data before and after that turnaround. And the average temperatures, they were lower, not a big deal, 5 Celsius. But those transient excursions, the number of panel operator interventions went down 75%. And they could get 4% max throughput through the unit, addressing the issue costing tens of thousands of dollars per day. So this is sort of historical use case. It's used extensively in refining. More recently, it's been used in the cement industry, where decarbonization is a really important topic right now. Most people don't realize it's something like 4 to 8% of the world's CO comes from cement plants, making material that's needed by our society. But the calcination releases CO2. It's endothermic, so you're combusting fuels to heat the process, typically coal. And so it's a very carbon intensive industry. Here's a calciner. I won't go through all the details. Again, an awesome presentation by a German company from our users conference last year. You can watch the full video here. But in a nutshell, they had a calciner running with high CO emissions, and it was preventing them from going to more alternative fuels. So basically replacing coal with waste streams. So you're not bringing that virgin carbon out of the earth and burning it to put in the atmosphere. But those waste streams had different combustion behavior, different transport behavior through the unit. So they're studying using the software, what was happening, tested various alternatives, came up with a novel retrofit that has never been implemented before. They went ahead and implemented, and they wanted to see, like, is this successful? So here what I'm showing is the monthly average CO emissions over a multi-year period. They made the modification, implemented it, and a couple things happened simultaneously. The CO, the carbon monoxide emissions, went down 70 to 80%, excuse me, which is a really good thing. But they were able to do it while also increasing the fuel substitution an additional 22%, replacing coal with waste streams, with refuse-derived fuels. This paid for itself, not the simulation, it paid for the entire retrofit in less than 6 months. And just to give you a feel of what's being done in the sustainability space, I have this pretty picture on the right of a trash dump, and people are asking questions like this. What if the carbon in municipal solid waste, and I'm sure there's people logged in here from around the world, so trash, rubbish, garbage, whatever that term is, what if it could be recovered and put to use? This is a question asked by Thermochem Recovery International, TRI. They developed a gasifier. There's many places this story is told. A lot of technical details are in this 2019 Users Conference presentation by Ravi Chandran. They developed the gasifier. It was implemented at Fulcrum Bioenergy's Project Sierra out in Nevada, a plant that converts 500 tons per day of trash to net zero carbon fuels, including sustainable aviation fuel. Super exciting things happening. So that's Barracuda Virtual Reactor. That's some sample uses and outcomes. I'm sure you want to see the software. So at this point, I'm going to hand it over to my colleague, Sam Clark. Sam is the Barracuda Virtual Reactor project manager and product manager, and he's going to show you the software. So Sam, I'm going to step out of the screen and over to you.
Yep, thank you, Peter. Yeah. All right, so let me drop out of PowerPoint, and Sarah, if you cannot see the demo screen, let me know. Otherwise, I will assume we are good to go.
Yes, it's great.
Okay, great. Thank you very much. Yeah, so so Peter gave you a great high-level overview of how Barracuda is used, what the applications are. And what I'll do is just give you a short tour of the software itself. So here I have the APA version of Barracuda up and running on a Linux system. Barracuda is also supported on Windows, so depending what operating system you use. And what we see here is the graphical user interface. I have opened up an example project that we use in our new user training. So if you attend a new user training class for Barracuda Virtual Reactor, this is one of the examples you'll work through, and it's a coal gasification example that illustrates a lot of the capabilities of the software. So the screen that we're looking at now, this is the grid generation screen. Barracuda has a grid generator bundled with it, and this user interface for defining your grid lines. Barracuda uses STL files as input for the three-dimensional geometry, and the user defines a computational grid to define the resolution of the Eulerian calculations. And so after you do that, you can view what your grid looks like. So I'll go ahead and click one of these buttons. You'll see this throughout the Barracuda GUI. We have these buttons that are integrated to open TechPlot with some predefined views that people use as they're setting up their project and post-processing their project. So in this case, here's what the geometry looks like after we've put our grid on it. It's three-dimensional, and essentially all Barracuda simulations are three-dimensional and transient in time. So as we start looking at these results and the setup, just keep that in mind. We've defined a lot of quick macros to look at different aspects of the model. So while we're looking at our grid, we can look at a transparent view. We can double click some of these. We can see the grid lines themselves. We can see the original CAD model in STL format, just a lot of kind of convenient macros that help people work efficiently. If we keep looking down this project tree, and the way that the Barracuda GUI is designed is there's this tree on the left, and if you work from the top to the bottom, you should have a completely defined project by the time you get to the run page. We'll go down a little bit. Let's look at base materials. As Peter mentioned, a lot of Barracuda simulations have historically been compressible simulations, and this is an example of a compressible one. So we have a number of gas species, and the number is not limited in any way, but typically people might have 10 to 20 gas species in a Barracuda model, and these could all be involved in chemical reactions. They can be fed at boundary conditions, all those sorts of things. And then you can also have solid species, liquid species if your particles were coated in a liquid, for example. So here, if I open up one of these, you'll see that Barracuda does allow the user to input a lot of physical properties that are needed for the calculation. And so there's a whole user interface for doing that. People can define their own materials if they need to, or you can pull materials that are in a built-in library that's included with Barracuda. And so a lot of times you'll find that the materials you want to use are already there. It can just be pulled in to the project material list. Let's keep working our way down the tree. If we look at some particle stuff, one thing I wanted to point out is drag models. And so for people who are modeling fluidized beds or other systems with gas solid flow or liquid solid flow, the drag model is one of the more important empirical models that you'll have to use. Barracuda has a lot of different drag models built in, and it also has the capability of users defining their own drag models using this sort of user-defined expression interface. And so it's quite flexible, and our users have been very very creative and using these sorts of things to solve a lot of unique problems in their systems. If we go to particle species, there's no limit to the number of species that you can have. And so in this example, we have an initial species for char that's in this bed. We have a different species for coal that's being fed into the bed. So I'll just take a look at this one. Species can be composed of any number of materials. And so in this case, we're saying that our fresh coal is 5% ash, 45% carbon, and 50% volatile material that would escape from the particles as they get heated up. And so this is just one example of how you can use multi-component particles. Peter mentioned that size distribution is a big deal in these types of systems. And so Barracuda comes with the capability of defining any size distribution that you want. And so typically people will measure their particle size distribution. They'll put the tabular data into Barracuda. And then this is another instance where we have a button that's integrated with TechPlot so that you can visualize your size distribution in that way. Okay, the next thing I wanted to point out is boundary conditions. So for people who are familiar with CFD, boundary conditions are an important part of any model, right? And so in Barracuda, we have a number of different types of boundary conditions that can be used. Pressure BCs, where you define a constant pressure or a time varying pressure at a specific location. In this case, we're using it on our cyclone inlets. We have flow BCs. Typically, these are where you're defining an inflow of particles and fluid. It also has the capability to define an outflow if you have particles exiting a system at a specific location. That can be really useful. Here, we'll open up one of these just to kind of show you what this interface looks like. This is pretty typical for all of the different kinds of boundary conditions in Barracuda. Usually you'll set some sort of spatial region. In this case, this is where our fresh coal is being fed into this system. And so you can specify it graphically, or if you know the exact location, you can type that into the interface as well. You can gather a lot of information at boundary conditions using a tool that we call flux planes. And so this will measure fluid flow, particle flow, energy at that location. All sorts of information is available there. You can specify what fluids are being fed in at a specific location. So here we have a mixture of nitrogen and oxygen. Those are there, and they can react if you define reactions that involve those species. You can define how particles are being fed into the system, what mixture of particles, what is their flow rate, all those types of things. Barracuda also supports fluid tracers, which are used to measure fluid residence time, for example, and visualize fluid flow in a unique way. I'll go ahead and skip the rest of these. They're all pretty similar, but they do have their own unique strengths depending on what you are trying to model. If we jump down to chemistry, this is an important part of a lot of Barracuda simulations, right? Most people who are running Barracuda have chemical reactors that they are interested in modeling. This would look pretty familiar to most chemical engineers. We're defining reaction rate coefficients, and then those rate coefficients can be used in the reaction rate expressions that define how each reaction is taking place. Barracuda has a number of built-in forms that are common for engineers who are modeling these types of systems. This is an example of an Arrhenius form. We also have a special one for catalyst deactivation, for example, or you can do, again, you can use a user-defined expression interface for this type of, for reaction rate coefficients. And so this can be very flexible as well. If you have reactions that have kind of complex equations that define the rate, this user-defined interface is very flexible and can handle those types of things. If we look at the list of reactions itself, again, this is kind of typical for Barracuda. Some people have more reactions, some people have a little fewer, but I'd say most of the time, we're kind of in the 10 to 20 reaction sort of range for what people are doing. If we look at this sort of interface, a lot of people use stoichiometric reactions, and there are a couple of other options in the GUI, but this one's pretty common. And so you would define, okay, I have 2 moles of carbon plus 1 mole of oxygen going to 2 moles of CO. That's happening at this rate. This is my rate coefficient K0 times the concentration of O2. So the input is pretty familiar to most chemical engineers. If we skip down to data output, there are a lot of different ways to get information about your system out of the software. We have flux planes, which are similar to the ones that we saw in the boundary conditions, where these will tell you flow rates, the mass flow rate, the energy flow rate, those types of information at any point in the simulation or any location. Visualization data gives you a lot of control over what information you're getting in TechPlot for Barracuda. And there's a lot of particle information available, a lot of cell-based information available. And so depending on the system you're modeling, there's a lot of flexibility there. As I mentioned, Barracuda simulations are inherently transient simulations. And so they'll start at time 0. Typically, you'll start your bed fluidizing, and then you'll let it run for some period of time to reach a steady state condition. And so we do support some time average data output, and this can be really useful for making engineering conclusions to compare multiple different simulations. So you can look at time average fluid temperature, time average fluid velocity, time average composition. Those sorts of things can be really useful from an engineering perspective. A couple other things I'll point out. Data points are very commonly used by a lot of our customers where they want to model things like thermocouples or pressure transducers that in their real system would be giving them high frequency output. You can mimic that numerically using data points at any point in space in the simulation. Another model is not being used in this example, but a lot of our users have used a wall erosion model to analyze different configurations and try to figure out what would reduce erosion on mechanical components or on the walls of systems. So that's a pretty common thing that some people have used. If we jump down to run, as I mentioned, if you walk down the tree and you get to this point, you should be in good shape for running a simulation. As Peter pointed out, Barracuda supports GPU parallel calculations, and the vast majority of our users do this because it can make your simulations run so much faster if you accelerate it with a GPU. So I'll go ahead and start a simulation here. I'll start it in multi-GPU mode just to illustrate this. So if we use 2 GPUs and start the solver running, you'll see it does a little bit of initialization work. It sets up the particles, checks out a license, and then starts time stepping through the case. And so this is typically what the Barracuda solver will look like. It'll start doing one time step at a time and progress through that simulation. And as it runs, we can start to look at a few things that it's doing. So here, one common thing that people do is they check their boundary conditions, right? And this is always a good idea. Make sure your boundary conditions are set up correctly. And so we have a few colors that are kind of a standard for what our users are used to. So as I mentioned, pressure BCs are on these cyclone inlets here. So these are these yellow surfaces. We're using a feature of Barracuda called BC connections to return particles from the pressure inlets down to the dip legs on these cyclones. So these are these lines that you see drawn here. The bright pink surfaces here are being used as thermal walls. And so these are locations where the wall surface temperature has been specified by the user and is transferring heat into the system. And so this is like tubes that steam would be flowing through, for example. This red patch on the left, this is where our fresh coal is being fed. The big red patch on the bottom is a uniform injection of steam. And these points with arrows coming off of them, this is a set of injection BCs that's being used to model a gas sparger with hundreds of nozzles. And so this is a pretty common practice for people who use Barracuda as well. A lot of times you have large gas spargers that have many, many nozzles. And so this boundary condition is really great for modeling those types of things. Okay, I'm going to go ahead and close that. And we'll just leave that running, no big deal, but I will go ahead and switch over to a case that has been fully run already, and that way we can just show a little bit of what the final results of this case would look like. So I'm going to go to the post-run part of the GUI and click View Results. And what you'll see is it'll open up the most recent results from the simulation. In this case, ran out to 100 seconds, and so we have results there. The default view is to look at particles colored by volume fraction, which is a convenient way of thinking about their concentration throughout the spatial domain. And this is another area where these quick macros on the side are really handy. So we can look at the particles by speed, we can look at the particles by size, particles by residence time, right? There's all these kind of default views that are really easy to access. We also have similar things for the cells. So we can look at the cells by pressure, cells by velocity, and so forth. So a lot of flexibility built in there. One other thing that TechPlot for Barracuda supports is the idea of using layouts. So I'll go ahead and load a layout that I defined already, just so you can get an idea of other types of views that can be accessed in the system. So here, apparently my file system is really thinking here. And there we go. Sorry about that. And I'll say, no, I don't want to save those changes, but I do want to load this layout. So here, this shows a couple of examples of other types of visualization that people use pretty commonly in Barracuda. The middle view is what we call a slice. And so here we can look at data on a single plane within the system. And TechPlot has some really nice features for slices. You can kind of move them graphically and explore what the temperature looks like at specific locations. They have a nice thing where you can animate a slice and kind of have it do an automatic sweep kind of back and forth through the system, so you can get a really good idea of what's happening in a three-dimensional sense throughout the whole vessel. So there's a number of really good features available there. The rightmost view here, we're using something called isosurfaces. And in this case, we're drawing three-dimensional surfaces at specific gas compositions. So in this view, we're looking at the concentration of methane in the system, and we can get a really good three-dimensional idea of where the methane concentration is high, where the methane concentration is low, those sorts of pieces of information. As Peter mentioned, visualization is not the only thing you can do with Barracuda results. We also have options to output all of the data to text-based format, and so a lot of our users do that. They'll export it and analyze it with a script that they've written, maybe in MATLAB or Python. And then TechPlot also supports what they call PyTechPlot, which means that you can connect to a running TechPlot session and run Python commands and run Python scripts to do really advanced post-processing. So a lot of capabilities there. I'm going to go and stop the simulation in case that's what's using all my file system capability. And I wanted to mention a couple of other things just that users find valuable when they start using Barracuda. So one is all of our screens have a help button on them. We have a very detailed user manual that covers all of the features of the software. So the documentation that's built in is really strong. Our website also has a lot of resources, so I'll just go there real quick to point a couple of those out. One is we have a whole database of publications. So if you're starting to use Barracuda and you're wondering if someone else has done something similar to what you're doing, we have hundreds of publications that Barracuda users have written, and we have this list of them available on our website that can be really handy so you can see what other people have done. We have a whole section for webinars and presentations that talks about every new version of Barracuda typically has an associated webinar that goes over what are the new features. We also have webinars from our users about how they're using the software and what they're doing. And then we do have a whole support site of the software that if you log into it, you can access all of the training materials, a bunch of support articles on very specific topics related to Barracuda. So a lot of resources available, and as Peter said, our goal is to make sure that Barracuda users are successful and getting the most value from the software that they can. So that concludes the demo, and I'll hand it back over to Peter and Sarah, and we can wrap up.
Well, thanks, Sam.
Yeah, thank you guys. Thank you for your presentation, Peter, and the demo, Sam. With that, I think we can open the Q&A session. Please, everyone, continue to type in your questions into the questions panel. And for now, I will read the ones that we already have. First one, can it be utilized for slurry reactors equipped with single or multiple impellers?
That's a good question. That would be tricky, and you can step in. But so slurry reactors, yes. What Barracuda does not have is moving components, so we don't have the moving impeller. There are some ways to handle slow rotations if the whole domain's rotating. We have had some clients want to do it anyways and have put sort of transient set of boundary conditions going around to try and mimic that type of flow, but no, not natively. It's not built for moving impeller blades at this time.
Okay. And what are the models used for solving gas or liquid phase and solid particle phase? Is it two-way coupled model?
Okay, so the gas is Eulerian, the particles are Lagrangian, and they are bidirectionally coupled. So it's the gas or the fluid that would drag the particles. At the same time, those particles are occupying a volume and affecting the pressure drop in the fluid.
Okay. Which contact models are available to the model to model the collisions between the particles and between the particles and walls?
Okay. So, and then here is I'm gonna answer that, and then, but before, let me go to the high level. What I want to point out is that Barracuda Virtual Reactor uses a 3D MPPIC, multi-phase particle and cell method. So I point that out to make a distinction between it and DEM. DEM is going to look where each particle contacts another particle and then computes, bounce. What Barracuda does instead is it handles that through various models. I think the person who asked that, by the way it was phrased, understands that. But for the broader audience, we don't know where, we purposely don't try to compute where every particle is touching every other particle. Instead, we say, okay, a particle is going into a region. What is the probability of an impact? And it cares less which particle it hit, but will it hit particles? And then you'll have various models that take over. So there's a normal stress model that takes over at the denser phases. You'll have BGK type collisional models that in more dilute phase. There's a few different ones there. When a particle hits a wall, now we do know the particle hits a wall patch, we'll know the angle of impact, and so we can have a restitution and a scatter function for that the user has control over as well. But the reason this matters is because by using those models instead of directly computing, does two things. It reduces the computational complexity tremendously, which lets us go to that full industrial scale. The second is it doesn't require super small time steps for that collision detection, which again lets us move out much quicker. So this is an important fundamental part of how we're able to go to full industrial scale. Anything to add on that, or?
Yeah, no, I agree, and I think that is the important point is kind of these probabilistic and statistical based models that Barracuda uses do enable us to do these industrial scales. We know that we're leaving out some of the particle to particle details, but that's okay, right? We've done a lot of validation of the model results against industrial scale data, and these assumptions are acceptable. The other thing I would mention is, as Peter mentioned, we have the particle stress model that kicks in at high volume fraction. We have wall bounce parameters that are user controlled, and there are some other collisional models that are available in the software. And we have published papers on these, so we can always follow up with anyone who's interested in kind of the numerical details of those models.
And this might be overkill on one question, but I would just add it. I think it's super important to use the right tool for the job.
Yeah.
So if you're in a situation where every particle, touching every particle matters, DEM is great for that. In fact, I believe Altair has EDEM, which my understanding is the leading DEM software.
Right, exactly.
Use that when a particle hoppers, avalanche, the direct, when it's dominated by direct particle contact. When it's dominated by the fluid particle interaction, such as fluidized beds, this is where Barracuda comes in.
Yeah.
Mm-hmm. And you guys talked a lot about particles. How many particles can Barracuda Virtual Reactor handle?
Yeah, there's really no limit to that. Every time I get asked this question, it's a different answer over the years. So Barracuda Virtual Reactor takes the physical particles in the system, which in some of those FCC regenerators where your average particle size is under 100 microns and they're 10 meter plus diameter, you have we did some math, 10 to the 16 plus particles in that system. We will model that by some lesser number of computational particles. I used to say that number is on the order of 1 million. About 5 years ago, that was averaging more like 10 million. We've seen some simulations with 100 million plus computational particles now. And as we move to GPU and multi-GPU computing, and as NVIDIA makes their GPUs more powerful with more memory, And then the streaming memory feature, there's really not much of a limit. I'd say, you know, the low 100 million is still is practical today in terms of computational particles.
Mm-hmm. And since you mentioned GPUs, is GPU hardware required, or which GPUs can be used?
Yeah, so I can speak to that. So yeah, if you want to use GPU acceleration, there is a requirement that you would need a GPU, and it needs to be an NVIDIA GPU. So the way that the programming is done for the Barracuda solver, it uses the NVIDIA CUDA language, and so NVIDIA GPUs are necessary for using that feature of the software. And as I mentioned, the vast majority of Barracuda users do have GPUs, and they use them for the simulations just because it makes such a difference in the time scale of the simulation.
Mm-hmm. Yeah, practically speaking, it is used for most of the time. It's not necessary, so people who want to try the software and you don't have a GPU yet, by all means, you can do a lot of the training examples without a GPU. In fact, what's a little ironic is the code we have today without GPU is the same, or actually it's better than the code that we had before a GPU release that was still solving a lot of these problems.
Yeah.
But with GPU now, people are running bigger problems, more complexity, more chemical reactions and so forth. So it's not required. It is highly recommended, and we can help. We have some recommendations on our site as to which GPUs to use. Yeah. We have various benchmarks, so talk to us if you have questions about that.
Okay, great. And then there's one last question. Can multiple individual reactors in series be created with interdependence of one on the other?
Oh, okay. So I guess as with most questions, it depends. If we do have people who within a single Barracuda model have put vessel 1, which is like connected to vessel 2, sometimes with like a standpipe or a transfer line. And so depending on the number of cells that you can handle and the number of particles that you can handle with your computer, you could certainly put multiple vessels in series within a single Barracuda model. Other users, if they have vessels that are too big or too complex to do that, you can use the information from flux planes. You can measure what's coming out of one system. You can use that as the input to the next system as you're setting that up. So it just kind of depends on what the system looks like. But if you could fit it all in one model, that would probably simplify your life so that you wouldn't have to do a whole lot of work on the boundary condition side of things.
Yeah, and I find it depends what you're trying to learn from the calculation, right? So if you're looking at the overall dynamics of the whole, do that, right? If you're trying to optimize each vessel, typically they'll build a detailed model of each vessel first, and then might try that together.
Yeah.
The last thing I'd add is you can physically connect them, like with that standpipe, but in some cases you might want to virtually connect them. So you, in the same Barracuda virtual reactor model, you could have vessel 1, vessel 2, but instead of physical connection, you can have an outlet from vessel 2, track what's leaving there, and use the boundary conditioning connector feature to say the particles that leave here are entering over here without modeling that transfer line. Yeah, you can even put a filter function on that. Maybe that goes through a cyclone first, and the fines are lost, and the other ones come back. So it's all possible. It depends what you want to accomplish with the model.
All right, great. So this seems to have been. Oh, actually, there's another question coming in right now. Can we use dissolving and condensation and evaporation, like mass transfer from particle to fluid or fluid to fluid?
Oh, okay, yeah. So depending on exactly what you're trying to model, yeah, typically you can do that. So in Barracuda, if you have a liquid material that's on the particles, that liquid can evaporate from the liquid film into the gas phase, and there's a built-in evaporation model to handle that.
And it works both ways.
Right, it works both ways.
Evaporation or condensation, depending on the condition.
Yeah. Exactly, yeah. And then also for, you can use chemical reactions to do some things as well, right? If the liquid is dissolving the particle, you could potentially define a chemical reaction that accounts for that. So hopefully I addressed the question there. Yeah.
And if we're not getting any of these, we got our contact information up there. Ask us questions or ask your Altair, your account manager, and they'll put us in touch, and we'll directly answer the questions, or if it's easier to try it, feel free to, you can learn more on the Altair site. We got some information on this page, or consider joining us for a training class and trying it yourself.
Yeah.
Yes, yeah, for sure. Note down here the contact information for CPFD. If you have more questions later, or if you have so many questions that it's too long to type it out, contact them and they can schedule a more in-depth discussion with you. And since this was the last question, it looks like, I just want to refer again to the CPFD software for more in-depth or other content, as well, of course, as our Altair resource library. There you will find a little bit more selected amount of videos right now that, you know, might be better for the introduction, you know, if you're new to the software. And then, of course, you find all of the materials on the CPFD software. And with that, I think we can conclude today's webinar. Just a reminder that we recorded this session as well. So you will get an email with the recording later, and you can then watch it again or share it with people that you think would be interested in that. And you can, of course, find it in the Altair resource library. And with that, I want to thank you again, Peter and Sam, for your presentation. This was so great and super interesting. Thanks for helping us make the world a little bit more sustainable, and, you know, hopefully help our customers to do so as well. And with that, I thank everyone for joining, and thank you for your time, and see you at the next one.